Thanks for joining us this afternoon, and I first want to acknowledge the student organizations that really put this together, and the student leaders are all in the room. You know who you are. Thanks to the Environmental and Energy Law Society, the International Law Society, and thank you to the Ocean and Coastal Law Journal. And thanks to our collaborator, Professor Mayewski, Director of the Climate Change Institute at the University of Maine, who made a 4-hour drive to get here to be with you today. We're here at a moment that feels like a tectonic shift. Our new president seems to be acting upon his America First energy plan, where he stated, we're going to cancel the Paris Climate Agreement. We're going to stop all payments of U.S. tax dollars to United Nations global warming programs. So from multiple standpoints, from international law, U.S. foreign policy, science-based agreements, and even objective facts, we appear to be in the early days of a great unraveling. This is the context of our subject today, which is law, science, in all caps, and policy of the Arctic. My fellow speaker and I believe that the facts, not alternative facts, the facts of science must drive Arctic policy and law. Why does this matter? Well, consider what effective policy professionals do. They clarify goals, appraise trends and factors, that's scientific thinking. They make projections and they devise alternative futures for our society. And then the law is where policy grows up. It's where it matures as prescription and ultimately applied. Thus, law and policy are interrelated, and science is the sinew, particularly when we're talking about the Arctic. Science is not new to the law, not to lawyers, nor scholars, nor judges. In 1899, Oliver Wendell Holmes was Associate Justice on the Massachusetts Supreme Judicial Court. He gave an address at the New York Bar entitled Law in Science and Science in Law, where he said the practical study of the law ought also to be scientific. He said, I have in mind an ultimate dependence upon science because it is finally for science to determine, so far as it can, the relative worth of our different social ends. Years later, 1943, writing in the Yale Law Journal, Mars McDougall and Harold Laswell wrote, effective training in scientific thinking requires that students become familiar with procedures by which facts are established by planned observation. The policymaker needs to guide his judgment by what is scientifically known and knowable about the causal variables that condition the democratic variables. They then offered a seminar called Law, Science, and Policy in 1947. I think Jeff Thaler was in the class now. That's how they look.
I was honored.
You were honored. Law and science as instruments of policy and private policy with reference to selected problems of property of politics. From this early set of classes, this curriculum emerged a method we now know as policy sciences, which is an inspiration for a joint course that we are planning to offer with Professor Thaler and with Professor Mayewski's group in Orono. This is because the scientists whom Professor Mayewski and his colleagues trained in Orono should understand law and policy, and our students of law and policy here must understand the relevance of science. Now to the Arctic. Arctic law, science, and policy is newly important for me. President Grimson of Iceland said, when he was here, that Maine is the eastern pillar of the U.S. Arctic strategy. And then a few months ago, Portland hosted the Arctic Council, the leading intergovernmental forum promoting cooperation and coordination among Arctic states, indigenous peoples, and other inhabitants. This coincided with the presence of Mayewski, an important shipping company from Iceland that is in large measure driving developments in maritime business, along with the expansion of the Port of Portland and the prospect for new shipping routes. Maine's role as a high north trade link is generating opportunities for our workforce, our universities, our research institutions. This has to do with science. Consequences, for example, of abrupt climate change you'll soon hear about. and the dwindling sea ice that we'll also hear about. Well, this is leading to enhanced human activity, including commercial shipping, cruise lines, oil and gas exploration, and mining. Change. The consequences of cryospheric changes are causing states and non-states to assert more intense claims to Arctic resources, with the prospect of melting ice becoming a source of conflict between and among polar and non-polar states. So the question for us in this room, lawyers and policy professionals, is how will the Arctic be governed? How will the Arctic constitute a process which is driven by an ever-intensifying process of claims, evolve in a context shaped by new cryospheric conditions? How will power be allocated, structures of authority designed? Who will be the decision makers, and what will be the procedures for that process of human beings making choices that we know as law? In addition to the A5, what are called the A5 group of littoral states around the Arctic Ocean, there are institutions that are increasingly at the center of this process. This includes the UN Convention on the Law of the Sea Architecture, because the Arctic, after all, is mostly ocean. The International Maritime Organization, the Nordic Council, NATO, and of course the Arctic Council. These institutions, which project policy, prescribe standards, and apply law, rely on science. The IMO relied upon science in appraising and devising the new Polar Code, which has just come into existence a few weeks ago. And the Arctic Council is driven by working groups, notably the group on the protection of the marine environment, known as PAIN. And now the United States is about to hand over the chairmanship of the Arctic Council, and so this is a key moment this year to promote and sustain the role of science in Arctic law and policy. Now the map here that I'm showing you, this slide, these are potentially new shipping routes. One is viable, one is partially viable, and the one in the center could be viable by 2030. So here in Portland, not too long ago, we had the Rhinegold Round Table, which was convened at the law firm of Mayewski to consider North Atlantic shipping opportunities for Maine. And last week, Mayewski and Greenland's Royal Arctic Line signed an agreement, and they both placed orders for Polar Code compliant container ships. Now, these are opportunities that Arctic science is providing. There are also challenges. Climate change, for example, affects the economy, health, infrastructure, societies, lifestyles, and cultures of the Arctic indigenous peoples. Indigenous land, the reindeer herding, access to fresh water, sea mammals, marine fish, and a range of subsistence activities are impacted. Also, the Arctic ecosystem encompasses land and sea, with much of the ocean component within maritime zones, but much of it beyond the jurisdiction of the 5 coastal states, beyond national jurisdiction. The Central Arctic Ocean is a particular challenge because it is beyond the jurisdiction of coastal states' ecosystem management. So a task right now in which scientists, lawyers, and diplomats are involved is working through a United Nations committee to achieve a legal instrument to protect biodiversity of areas beyond national jurisdiction, with a key goal of protecting the Central Arctic Ocean. Again, that is a science-driven law and policy process. Last October, we had the Maine Arctic Forum here. It coincided with the Arctic Council. And John Henshaw, who's sitting here in the room, who directs the Maine Port Authority, said at the time, I took notes, John, given the Arctic Council is meeting here this week, he said, there's an opportunity to understand the interface between science and policy. And John said he thinks it's a moment in time that we have to help shape the future of the North Atlantic in this region, and he's correct. The fundamental problem is going to be to balance exclusive interests to ensure a greater common interest of the Arctic for peoples and states, and this will require a robust relationship among science, law, and policy. Anybody who's been through first-year law school knows that we have something called evidence. Evidence, defined as the available body of facts or information indicating whether a belief or proposition is true or valid. And a fact is an actual occurrence, an actual happening in time, space, or an event that is mental or physical. Yet we suddenly seem in retreat from facts and from objectivity. So have we returned to what C.P. Snow, the novelist and physicist, once called the two cultures in the scientific revolution? He lamented this in 1959 at Cambridge University in a famous lecture. C.P. Snow said, the two cultures, one fact-based and the other imaginary, rarely communicated, and if they did, it was usually at cross purposes. There was a schism. Well, that schism between science on the one hand and policy on the other seems to have reopened, and is a trend that we need to reverse. So with that, let me introduce our friend and colleague, a real scientist, Dr. Paul Mayewski, who's director of the Climate Change Institute, distinguished professor in the School of Earth and Climate Sciences, the School of Marine Sciences, the School of Policy and International Affairs, and the School of Business at the University of Maine. Paul has led more than 55 expeditions to some of the remotest polar regions and the high-altitude reaches of our planet. He's published more than 400 scientific articles, received numerous honors, has led major international climate change research programs in the Antarctic, Greenland, Asia, Arctic. He's published popular books, has appeared on CBS's 60 Minutes, Nova, and is a fellow of the Explorers Club. Paul, thanks for being with us.
Thank you. Thank you so much for the introduction. We're very excited in the Climate Change Institute about this emerging association between the law school and our institute, and obviously the two universities. I think we have between us remarkable expertise, which is going to make a very, very big difference for Maine. What I'm going to talk about today is the role of the atmosphere in climate change, and in particular, extreme events. The purpose of the presentation is not to tell you everything there is about climate change, not to tell you many of the things that you probably understand already, but perhaps to indicate some additional highlights that don't necessarily get into the media. Despite the fact that I've had the opportunity to spend a lot of time with the media, these are not necessarily things that always come through the story. I'm particularly happy to be speaking to this group because of two reasons. Number one, just as humans, we are all going to experience change. We are already as a consequence of climate change. In fact, will define the 21st century. So it's essential that we understand what, in fact, is in store. Some of it is pretty gloomy. Some of it, in fact, will open up opportunities. And in a place like Maine, there may very well be a lot of opportunities, as already suggested by Professor Norchi. The other is that, of course, you all are in a fields related to law and policy, something that in our institute we know nothing about, something that we, however, understand as scientists is critically important. And it's essential that we translate to people like you who will be making decisions in the future based, we hope, on facts, that you've heard the full range of discussion, and that you realize that there are ways in which you can actually even interact with the data yourself. So I'll go through a sort of a very short introduction to perhaps a little bit of the adventure, and then I'll gradually talk about climate change, end up talking about the Arctic a little bit. I've given a couple of other presentations in Portland, and most of those are on the web. I can direct you to those for more detail. And then end up talking about climate change philosophies and where we're going with that. So I've made a big point of mentioning the atmosphere. The atmosphere, if we could have only measured one thing in the climate system, it would have been the atmosphere. It wouldn't have actually been temperature if we could only measure one thing. It's fortunate that we were measuring temperature because we realized that the temperature in general of the planet has been increasing. But if you really want to understand how heat moisture and pollutants are transported around the planet, you really need to understand something about the atmosphere. The reason that it tends to be warm at certain times of the year, even in the middle of the winter, in Portland is because the air comes from the south. It's as simple as that. When it's cold, the air comes from the northwest or the northeast. In addition to the atmosphere transporting heat, moisture, and pollutants, it also drives sea surface currents, particularly important, and also has a tremendous impact on sea surface temperature. The ocean then takes these changes in heat and transfers them much, much more slowly around the ocean basins. But the original signal is really embedded by what happens in the atmosphere. So obviously, if you warm the atmosphere, it has an impact on the ocean and everything else. So I've spent the last 40 plus years, as was mentioned, running expeditions all over the world. These little dots show you some of the generalized areas that we've worked on every single continent. What we've used, and this sounds perhaps sounds a little bit academic and esoteric, but we've used ice cores. We drill these columns of ice in all over the world, everything from Mount Everest to the interior of Antarctica. From these, we can go back literally storm by storm, year by year, decade by decade, and in some cases we've even looked at ice that's more than 1 million years old. We do this because the instrumental record, the recorded record of climate, in particular temperature, barely goes back 100 years, and in most places it only goes back 40 or 50 years. And sometimes there's additional information about precipitation, but the record is not very long. With the advent of the satellite era as of the late 1970s, we have a remarkable understanding of how the planet operates. But we need to go back farther in time. Why? Because the last 30 years, the last 100 years do not tell us enough about the dynamic range of the climate. How much can it change and how fast can it change? And that's particularly important for us to understand. So let me just tell you a quick story, one little adventure story about atmospheric circulation and how ice cores, we actually ended up being able to study ice cores, or study atmospheric circulation using ice cores. This is a picture from Ladakh in Himalaya, and Charles and I were just talking. We realized that he was in Afghanistan, and the same time that I was in Ladakh, we could literally see each other because I was high enough up, and he was down in a big open flat area, no doubt. But these are the people who live in the Ladakh Himalaya. I went here because it's a long story. There were literally no satellite imagery. We had no form of communication that we were allowed to bring with us, and we had no maps. We weren't allowed to carry maps. But I found in an old book a glacier that I thought might very well be a good glacier for us to work on. And I won't bore you with all the requirements, but they've obviously got to stay cold for the record to be preserved. So we took 6 weeks to actually make our way to the site. We hired several people from the local village, and we made our way up over 3 500-foot ice falls, gradually up to 20,000 feet. It was quite an epic event. We recovered an ice core, not very long. It turned out it only went back about 20 years. But the purpose was to study one of the major phenomena on the planet, the Indian monsoon. During the summer, it brings warm air from the ocean and allows the Indo-Gangetic Plain to have agriculture. Too much rain, flooding. During the wintertime, you have cold air, cold, dry air coming off the Tibetan Plateau. And for the atmospheric scientist who figures out how, in fact, that monsoonal system changes, and more importantly, is able to predict how it changes in the future, that's really one of the most important things that an atmospheric scientist can do. We didn't do it on this particular trip. Nobody's done it yet. Somebody eventually will, and perhaps will be involved. But something very spectacular happened at that time. We were standing at 20,000 feet, and it turns out that there were air masses coming from the Tibetan Plateau, which should be cold and dry, air masses coming from the Indian Plains, which should be wet and have an awful lot of agricultural chemistry incorporated in them. And this is all very intuitive, I'm sure. You're all thinking to yourself, well, that's pretty obvious, that if an air mass runs over an agricultural region, it'll pick up sorts of chemistry. But just like the law, you've actually got to be able to demonstrate that this is really the way it operates. And sure enough, the snow was precipitating in this area, so it was dropping the chemistry down. We were at 20,000 feet. As soon as the snow stopped, we went quickly down to 10,000 feet, sampling the snow in the everywhere we went. In the process, we were able to basically get some Tibetan source fresh snow and some Indian fresh snow, and the net result was that we were able to come up with a signature for the chemistry. Now fast forward to about 3 or 4 years ago, and this NASA image, which actually portrays exactly what we were trying to do, but we were able to demonstrate it, and it has become a mainstay of our science. And in this actual reconstruction, you can see the hours ticking away. This is from 2006. This is a NASA image that shows you air masses swirling around the Antarctic, air masses swirling around the Arctic, air masses being transported off the Sahara, dust making its way all the way into the Western Hemisphere. And what they've done is to actually color the air masses. This is sea salt. It's the dominant chemistry for that. It's not the only chemistry. This is Saharan dust making its way, believe it or not, right into the Amazon. This green stuff is forest fire burning, making its way as smoke into the air, all the way down, if you look carefully, even down here into the sub-Antarctic. And then, unfortunately for us in the Northern Hemisphere, an awful lot of what gets incorporated into the atmosphere is sulfuric acid and nitric acids. Mixed in here are an awful lot of exotic chemicals too, so that you can actually specify directly where the air mass came from and give a history based on the chemistry that was produced. And then this is the only semi-data looking slide I think I have. But what we do then is take the chemistry, in this particular case, it's from a place in Greenland where we had a particularly long record, and we compare, for example, sea salt, the levels of sea salt that go up and down season by season, year by year. We compare it with the pressure over the planet, and you find very strong correlations, for example, between sea salt and the Icelandic low. And the Icelandic low is this pressure system in the North Atlantic that actually drives nor'easters into Maine certain times of the year. It turns out there's a direct correlation between sea salt and the Icelandic low that allows you to reconstruct back through time changes in pressure. Why do we care about changes in pressure? Because that tells us where air masses go in the atmosphere. So now we have a calibrated system. In addition to atmospheric circulation, we can also get from ice cores changes in temperature, changes in precipitation. We can understand past changes in sea ice extent, past changes in biological productivity on the land and in the ocean, past changes in volcanic activity, including and meteorite impacts, and past changes in the chemistry of the atmosphere. Greenhouse gases, soluble chemistry like sodium chloride, important trace elements like lead, cadmium, mercury that all have a very, very important health impact. So, with that as a background, let me just tell you very quickly, 2 minutes, some of the important things that we've discovered. These are lessons learned from ice cores. And again, it all depends on being able to get an ice core, the red dots, and understanding which way the air masses are moving because of what they transport, with the understanding that these air masses change season by season, and decade by decade, or century by century, they may actually shift quite significantly depending upon the extent of sea ice, the size of ice sheets, the amount of biological activity in the ocean, and a variety of other things. So what were we able to determine? We came up with the understanding that the climate can change very quickly. It's going to be one of the important things I'll get back to. We were able to demonstrate for the first time ever, when there was a big debate in the middle 1980s about acid rain, that in fact there was a direct relationship between acid rain and industrial pollutants coming off Western countries, and also later on Asia. We were able to demonstrate that lead has actually been emitted into the atmosphere by human activity for the last 2,000 years as a consequence, continuously, except during the Black Death, when 40% of the European population died. And this is important because lead impacts, as we know, a lot of our health. We've been able to find order of magnitude increases in uranium and arsenic in places like Antarctica, coming directly off open pit mines, open pit mining in Southeast Australia. We were the first to demonstrate that Chernobyl, which blew off here in whatever, I think 1987, took 18 months to go through the upper atmosphere and make its way to the South Pole. Able to demonstrate that the Antarctic ozone hole was not only that it had existed for thousands and thousands of years, but that the modern size of the Antarctic ozone hole is actually unsurpassed in at least the last 10,000 years. Critically important because that demonstrates that humans have had something to do with it, and also the impact of the Antarctic ozone hole on changes in the temperature of the atmosphere and therefore atmospheric circulation. We have worked on water resources in places like Chile by looking at glaciers in the high Andes, actually also most recently in Kyrgyzstan and Tajikistan in Central Asia. We worked on Arctic warming, which I'll talk a little bit about today. Disruptions to past civilizations. There are entire civilizations that have disappeared in a matter of years because atmospheric circulation systems that transport moisture have shifted and no longer brought moisture, more drought, marine productivity, sea ice extent, volcanic events, etc. Let me focus on just two things. Human impacts on the chemistry of the atmosphere and therefore temperature and health, and how quickly climate can change, because these are two very important things for you to keep in mind. It is not necessarily assumed that the way humans have impacted the atmosphere has necessarily impacted our, and certainly water, that it has much of an effect on health. In fact, I think many people assume that because we had a Clean Air Act, which did a great job on sulfuric acid, that we've cleaned everything up. And when I was a kid, all the lakes were polluted, everything was a mess. It's gotten much better, but we are far, far from the clean atmosphere that we experienced as humans a couple of hundred years ago. So, number one, I present this all over the world. There are skeptics in the audience. Nobody has ever argued about this. These are the undeniable human impacts. There's no doubt about it. And these all come from ice cores, except for human population, which is counted in a different way. So CO2 levels have risen dramatically. First, let me tell you, this goes from today roughly to 5,000 years ago. The only reason that I didn't extend this back almost 1 million years is that you would never see the last 150 years on the plot, and you would never see the fact that everything goes up. And these are all the things that go up. Greenhouse gases, acid rain, toxic metals. You can read the rest for yourself. We live as humans in an absolutely unparalleled period. No human has ever lived through the sorts of changes in the chemistry of the atmosphere that we have experienced, and our grandparents and our great-grandparents. This is critically important because it impacts our health, it impacts the way, in fact, our entire quality of life and the way we're evolving. And I like to talk about, this sounds very depressing, but I'll tell you why in a moment. It's not entirely depressing, what I call the toxic climate cocktail. It turns out that when you warm the planet, you of course increase vector-borne diseases. In the case of Maine, we didn't have Lyme ticks in 2000, now we have Lyme ticks almost everywhere. And the rate of Lyme tick infection has increased dramatically in the last couple of years. It ends up giving us drought, flood, and storms because of the changes in atmospheric circulation produced by temperature that I'll talk about. Then we have particulates in the atmosphere that change our respiratory capabilities, dramatic increases in asthma, neurological diseases, including things like autism, which is directly related not only to, but is contributed to by relatively unsafe levels of cadmium that are blowing around in the atmosphere. It's a consequence of industrial activity, various cancers, and then of course all of the ecosystem upheavals, ocean acidification. There is no doubt whatsoever that we have created a very different environment than we experienced as humans earlier. So that's sort of it's undeniable, all of those things. Perhaps people might want to debate what the actual impacts are. We'll talk about some of those in a moment, but they're undeniable. We know these changes have existed. And without ice cores, we would have never been able to take it out over a long enough time frame to realize it's changed. So the next thing, let's examine why climate changes, how fast it can change, whether or not humans have actually, by doing all of these things, have impacted the climate system, and how much of a change is needed for how big a change do you need to really impact humans. And I'll go over this very quickly. It's all based on a program that I ran for a several-year period in the center of Greenland. It's about 10,000 feet up. And we drilled back in time 110,000 years. We're able to count back year by year the longest continuous record ever produced of change in climate. And from that, we learned some very interesting things. I'll give you a quick summary. Why does climate change? It's because of all these little cartoon characters. Where the Earth is with respect to the sun that changes. Greenhouse gases, which obviously capture heat. The way the ocean circulates that heat and other things. Changes in the size of ice masses and whether or not sea ice and icebergs form around them. Changes in the energy of the sun, which actually control the chemistry of the upper atmosphere, which determines, therefore, how much heat from the sun actually comes into the Earth or doesn't come in. Things like dusts, which can be contributed to the atmosphere naturally, but also by Dust Bowl type events, by urbanization, putting in parking lots, a variety of other things, and then things that we have no control over, things like volcanoes, meteorites. So these are the things that come together, and with this 110,000 year record, we were actually able to put that all together. So the next thing we learned is how fast can climate change? And it turns out that we were able to demonstrate that this is the jet stream. This is the summer position of the jet stream. This is the winter position of the jet stream. We were able to show that this position of the jet stream could change very, very quickly in less than a year or two, and in fact get locked into that state, more winter-like or more summer-like conditions for decades, if not centuries, and as quickly, in a couple of years, come right out of it. And along with that go massive shifts in storm frequency, precipitation, and temperature. This is a very, very important finding. It was, nobody assumed this was the way the climate system worked. We all assume that it changes very, very linearly and very slowly, and why does it matter? If in fact, as we believed prior to about 1992, the climate system operates over thousands and thousands of years, linearly but very slowly, it really doesn't matter what you put in the atmosphere. Greenhouse gases shouldn't actually change the temperature very quickly. Everything would gradually make its way through the system. It turns out that's not true. So the next question is, of the things that control the climate system, how many of them have we actually impacted? All the red stars are the answer. And it turns out that the climate system operates the way it always did naturally. It's just that we've put all of these things on speed, in effect, and dramatically changed the way they, how fast they can operate. Let me focus on two of them very quickly, because obviously we can't talk about climate change without talking about carbon dioxide. This is the carbon dioxide record going back 800,000 years from an ice core, which we did not collect or analyze. But you can see there's a range that it stayed within. And then all of a sudden, as of the last few decades, the levels have increased dramatically. Now we're well over 400, where the normal high was about 280. And this is the projection for 2100 up to as much as 900 parts per million per volume. Now, the fact that the magnitude is increased is dramatically important. What is, in my opinion, even more important is that this rise has occurred 100 times faster than any other change in the last 800,000 years. And that's really big, and that's why you get a fast, potentially fast response from it. The other thing that's important is methane. Methane is 30 times more effective in trapping heat, and the methane that is being released from Arctic warming, the decrease in sea ice, the warming and the release of heat from the ocean associated with that, coupled with greenhouse gas warming, is allowing much of the frozen ground, the permafrost, throughout at least coastal sectors and gradually more and more to release methane. This is not a fire that was actually produced with any human fuel. They simply dug a hole in the snow. The methane had been trapped under the snow, and they threw a match in and it caught fire. So it's remarkable how much methane is coming out and how effective it can be. And then, of course, the last question, how much of a change is needed to impact humans? The quick answer is, if you're in the wrong place, not very much. If you live in the Arctic and you are a native person in the Arctic, you know exactly how different your environment is compared to just a few years ago. There's no doubt. Their villages are melting, roads are no longer passable, one truck movement over a permafrost area creates a linear lake. Things are changing dramatically, but you know, we shouldn't be surprised because there are places like the Mesopotamian Empire 4,200 years ago. This is actually the scene of the last of Raiders of the Lost Ark when they're riding out by horse. This is the city that they're coming out of that in fact disappeared 4,200 years ago because of a small shift in atmospheric circulation patterns that no longer brought precipitation. And the very same with the Incan, the Mayan Empire, about 900 AD, a very, very rapid decline within a matter of years because of lack of precipitation. So let's see how warming, it's called global warming. Steve Schneider, American scientist, passed away a couple of years ago, was who coined this term. It was a phenomenally good term for the media. It's being used for a long, long time. It's now being converted to sort of to climate change, which is not entirely correct, because climate change has always happened. We should really talk about it as anthropogenically induced climate change, but that's not much of a soundbite. This was a better soundbite, global warming. And yeah, we are definitely on our way to seeing warming all over the planet, but thus far the warming has been confined primarily to the high northern latitudes of the northern hemisphere, and in particular the Arctic. A couple of places around Antarctica, and if anybody wants to ask an interesting question later, if you're careful, you'll see that this is blue, and it suggests that actually the Southern Ocean is cooling a little bit. This has to do with the Antarctic ozone hole, also produced by humans. But most of the primary warming is in the high Arctic, and we know this because using this software we've developed in our institute, you can look at the last 15 years compared to the previous roughly 20 years, and this is the anomaly you get. Let's look at this anomaly in more detail. It turns out that over roughly the same time period, there are parts of the eastern Arctic flanking Russia, which is where the sea route has opened up the most, where the increase in temperature in about a 5-year period is as much as 5 degrees centigrade, 8 degrees Fahrenheit. It's huge, absolutely huge. And the best way to think about it is that in terms of summer, although I didn't write summer here, this is annual melting degree days. It's another way of determining summer. It is the equivalent in this area of doubling the length of the summer. Now imagine if that happened in Maine, how different things would be here. It's going to be a while before we double the summer, but we've already increased the summer by 1 week relative to the last couple of decades. This is a doubling in the length of the summer. And if we go back and look at our ice core records and look for an analog for this event, the last time there was this much warming, it actually covered a much, much larger area, but this much warming and a doubling in the length of the summer the last time it happened, and the last time it happened this fast, in fact it was even a bit faster, was about 11,500 years ago during the transition between the last remnants of the Ice Age and modern climate. So we are experiencing something very, very unique in the Arctic. What does that mean? How does that translate into climate for us? If you live in the Arctic, you know exactly what happened. But if, in fact, you live to the south of the Arctic, what's happened is what was normally cold in the high latitudes is now relatively warmer. The mid-latitudes are a little bit warmer, but most of the warming is in the high Arctic. And it turns out that the temperature difference between the high Arctic and the mid to low latitudes, that difference in temperature determines how strong the winds are that blow from west to east across the northern hemisphere. The winds have rushed right across Maine. And the stronger the temperature difference, the stronger the winds. The temperature difference is now weaker than it used to be. The net result is that these westerly winds are taking a much more circuitous pathway, and there is much more exchange back and forth of air from the south, which is warm, air from the north, which is colder. And this is exactly what's happening The barrier between cold air and warm air is no longer this nice straight, relatively straight line. It's much, much more embayed. The more embayed it gets, the more it locks into position, and the more you get cold air in juxtaposition with warm air, the more likely it is you will have extreme events, major storm events, and that's exactly what we've been experiencing. So a lot of what we have seen in the last few years is a consequence of Arctic warming. And look at this. This is quite remarkable. December 30th, 2015, this actually happened since then. On that particular day, again, this comes from our software that's publicly available, the shape of the jet stream, instead of going like this, actually tucked right into the North Atlantic. And if you look at the temperature here, December 30th, the middle of the night, in the Arctic, the North Pole was above freezing, which is quite remarkable. All of a sudden, you're transferring all this heat back and forth. So, abrupt Arctic warming has happened. It is the first demonstration of an abrupt change event, demonstrating that climate does not operate linearly, number one, and therefore we see clear and present examples of climate change, in this particular case abrupt climate change, in the physical, chemical, biological, and social sense, of which I alluded to most of those. It definitely heightens our necessity for understanding how much change and how fast that change will occur in other places. And it's not just the Arctic. We're seeing changes in drought patterns all over the world, in particular places like the Middle East. One of the underpinnings for the Arab Spring was in fact warming that reduced the amount of moisture available in a farming region that didn't have very much moisture. And along with, as I demonstrated in the previous slide, along with this juxtaposition more and more of warm and cold air masses, we have more extreme events. Storms, droughts, floods, heat waves, etc. So, in my opinion, and many of the people say this, but I think we're one of the earlier groups to say it, climate change is a major security issue. It impacts our health, our economy, the frequencies of catastrophes. A lot of people like to call them natural catastrophes. Yeah, they are. They occur naturally, but we have increased the frequency and the magnitude, and it's certainly changing our geopolitics, with one example being the Arctic, other examples being where there is water and where there isn't water, and where, in fact, people will go to get it. So, in our institute, we've developed an initiative in the last couple of years. It's called Climate Futures. It particularly has a business term in it because we want people to understand this is not just a scientific problem, it's a problem, it's an issue and a prediction that impacts us in many different ways. And we've produced all of these software systems that allow you to interrogate physical climate, chemical climate, and superimpose them onto a map. Our intention is that communities, and we've introduced this in a workshop in Maine, communities can actually go to this and understand how much the climate has changed in their area. In fact, if you are at a cocktail party, you pull out your smartphone and you go to Climate Reanalyzer, and if there's a debate about whether or not the temperature has changed, precipitation has changed, you just go there and you can show them a beautiful picture demonstrating whether or not there has been change. And the change is not everywhere, as you saw from the last map. So the next thing is that we want to use this as a platform for people to evaluate vulnerabilities, assets, and yes, opportunities. In most cases, the world is not going to suffer a lot of opportunities, but there will be places where this will happen. I believe the population of Maine will double. As the Arctic opens up, as sad as it might be, there will be opportunities that evolve. Where you have crops being grown will change. A whole series of things will come up. And the opportunities that evolve from those things are directly related to people like you who can begin to think about the policies, the law related to it, and the technologies, etc., that will help us to achieve these opportunities. So, let me back up very quickly. I'll end in about 3 minutes. Let me give you a quick overview of what I call climate change philosophies. It's important to keep these in mind, I think. The first climate change philosophy, I hate to even really call it one, but the fact that climate change is a hoax. In particular, climate change is a hoax that was perpetrated by the Chinese. That didn't happen. I work in China. The Chinese actually found out about the change in climate from Western countries, particularly the United States. So I guess it is a hoax that's being perpetrated by the United States then, instead. But it's based on misinformation, anti-science, names like the Heartland Institute, which have tremendous amount of money coming from the Koch brothers, have specialized in misinformation. This is a philosophy. It's, in fact, more of an ideology than anything. And I'd be happy to talk more about it. The second is, modern climate is largely influenced by human activity, but the change is linear. This is what comes out of the Intergovernmental Panel on Climate Change. This is a remarkable document. It's produced about every 5 years. It's produced by a large number of scientists, policymakers, a variety of people who come up with the least common denominator understanding of climate. That's a very important fact. Least common denominator. That means that they're not looking outside the box. They're not looking for extremes, but this is in fact the fundamental framework from which we understand the climate system, based on piles and piles of papers, facts, etc. Now, despite that, there have still been climate change surprises that have occurred. One of these is the warming of the Arctic and the loss of sea ice in large parts of the Arctic. That was never predicted from IPCC because they never took into account abrupt climate change. Why didn't they do that? Because it hasn't really happened over the instrumental record. So there was no analog, no way to produce this in a climate model. Were they wrong? Were they foolish? No, not at all. Based on the science they had. Now we have an example of an abrupt climate change, and it changes the way we think. And with the release of Arctic methane and a variety of other things, we can expect these to occur in other places. So the third approach is sort of wait around, assume the climate is linear, and just wait for the next surprise. The surprises have been acid rain, the Antarctic ozone hole, greenhouse gas warming, pollutants in the atmosphere like lead, etc. The other one is climate futures. I wish I could say that we've solved everything. We're far from it. But climate futures is a way of approaching science, in this particular case, using transparent, publicly available software to scientists, everybody else, with the understanding that the climate operates not in a linear way, but in an abrupt way, and gives one the ability to understand, not at the global scale, because nobody lives in the global climate system. To say that the climate will be 2 degrees centigrade warmer by 2100 is very important, but that's not a way you can understand exactly what the temperature change will be where you live. It could be very different. If you live in the Arctic, it's 5 degrees centigrade already, and therefore take into account those things. Climate futures then goes on to utilize plausible scenario planning, which is not done in the climate sciences. Plausible scenario planning is conducted by military, business. It's a system in which you take into account short term, which is very important in the next 10 to 30 years. What do you think it'll be like? You actually go in your head to 2035, and you say, what do I think will happen between now and 2035? And you also look long term. Long term is important because sea level rise could very well take into 2200, 2300. And when it eventually gets to that date, sea level rise will not be that conservative estimate given by IPCC of less than 1 meter. It's going to be at least 3 meters, and it could very well be 8 to 10 meters. A big, big game changer, particularly if you're worried or concerned with developing infrastructures. It allows you to engage the full range of views, including skeptics, because you typically have 4 scenarios. And as I included climate change as a hoax in one of the ideologies about climate change, you can include the very same people in this plausible scenario planning. And you're effectively going and saying how you think the world will look over short term and long term. So this is the last one. We've begun to develop plausible climate scenarios, somewhat for Maine, but thus far we've been funded by USAID to work in Mali through National Science Foundation with our ice cores and many other things, climate modeling, to work in Central Asia. We've been doing the same sort of thing in the South Atlantic, the most productive marine environment on the planet. And we're also doing the same thing. This should have actually shifted over to South America, sorry, in South America. And with that, I'll end, and I think we have a couple of minutes for questions. Thank you.
Questions before the class comes in. So,
If you need to go, please do.
It seems like it's an issue issue. It seems like there's an issue with the air, right? The cold air with cold air, the hot air with hot air. And you talked a lot about this abrupt climate change. So the solution, we kind of know where it's going to go if we stay in path. But the solution not being that temporarily based on regulations, we shift the mass air lighter movements periodically to then kind of say, all right, well, we're going to change enough to sustain kind of where we are, as opposed to, so this is a regulation of toxins in the air, and we just need to do that until we find a more feasible option?
That's a very good question. And there are actually two answers to that question. If you are talking about pollutants like lead, copper, mercury, particles in the atmosphere, they stay in the atmosphere a matter of days. So if you, during 9/11, when aircraft were shut down over the U.S., that was the cleanest air we had in the U.S. in many decades for that time period. We can clean our atmosphere. You can't shut down everything. But theoretically, if you shut everything down, you can clean the atmosphere very quickly. However, this other issue, the exchange of cold and warm air, is really based on greenhouse gases. Greenhouse gases stay in the Earth's system, and the levels in the atmosphere will remain high for many decades, if not centuries. So the fact that we have more extreme events is a reality that we have to live with and understand, but we can use that understanding to predict where we will have storms, where the World Bank should invest money, what sort of legal issues will appear.